Welcome everybody to this session of the ACPMS seminar. Today we have the pleasure to have Amy Pang, who will speak about Markov chains from linear transformation and Hopf algebras. So Amy, all yours, please.
Thank you. Thank you very much to the organizers for having me here. So I'm going to talk about Markov chains and how they're related to like linear transformations and linear algebra. So this seminar is called Algebraic and Combinatorial Perspectives, right? And the perspective that I want to share with you is that if you have a linear transformation T on some vector space V, and there's some basis of V relative to which T expands positively, then you can actually interpret that data as a Markov chain on the basis of V. Okay, so I'll explain in more detail how that works later, but the main idea is that then you can use the linear algebra to study this probabilistic process, and maybe some probabilistic facts would also give you some new linear algebra facts. Okay, and there's actually a lot of work in the literature that makes use of this perspective. And what a lot of them do is they look at the eigenvectors and the eigenvalues of the linear transformation. And out of that information, they deduce something about the long-term behavior of the probabilistic process. So this is like a common application of the algebra to the probability. I'll say a little bit about that, but mainly I want to concentrate on a relationship that is less well known, which is that if you have a special type of subquotient V bar of V, and T induces some T bar on this V bar, okay, then there is some function that you can put on your Markov chain, such that the output is also a Markov chain, and that's called a projection. So I'm just trying to say, like, the subquotient data of on the algebraic side gives you a projection on the probabilistic side. And so that's a bit less well known. That's quite complicated, so I'll only be able to say the simplest version of that today. So that's the plan for the talk. And okay, good, people are asking questions. I was just about to say, I want questions. Okay, so the question is, what is a subquotient? I mean, take a quotient or take a subalgebra, or do like a quotient and then a sub, or a sub and then a quotient, like some combination of subspace or quotient space. Okay, but it has to satisfy some additional conditions, which I will talk more about when we get to the second part. So I want to spend most of the time on the first two parts, because like I would be really happy if this applies to some operators that somebody is studying and we get like some new probabilistic results out of this. Okay, so the third part is where I put like all the advanced features of this framework, as it were. And I don't really mind if we don't get very far through the third part. Like I can talk about that with individual people, like afterwards on this gather thing or on email or something. So let's spend like most of the time on the basic part. And so if there's things that I could say to clarify stuff, then let me know through the chat. Okay, I can read the chat from here. Okay, so the advanced features is all gonna, like, several advanced features will come together in this example from Jason Fulman. So I really want to stress that this idea can be applied to basically any positive linear operator, but I am mainly interested in the case when V is a Hopf algebra and my linear transformation is coproduct-then-product, in which case my Markov chain will model the breaking and then recombining of some combinatorial objects like card shuffling. And in this case, I have all the eigenvalues and sometimes also eigenvectors. But as I said, I won't say a lot about that because I want to mainly talk about the projection. And I believe the slides are going to be uploaded. So if you want more details on this, these links are clickable. Okay, and this is like over 100 pages of stuff altogether. So there's many details and examples if you're interested in that for after. Okay, so let's start with an example of this. Do the top to random shuffle, which is equivalent to it's some simplified model of the settling storage allocation. So this shuffle, it might look like a bit of a toy model, but it's actually related to something people genuinely care about. So you have a deck of n cards like this. And at each step, you first remove the top card. So I'm going to remove this red one. And this leaves me with a deck of 3 cards. Okay, so this removed card, the second step, I have to reinsert this card. And I can put it anywhere in between these remaining 3 cards. So they're including at the top and at the bottom. Okay, so that means there are 4 possible positions. And I choose from these uniformly, meaning they all happen with probability 1/4. Okay, so for example, I can choose this one. This is one of the possibilities. Okay, and let me show a few more steps of this. So the next step, to do the next step, we would remove this orange one. Okay. And then it would leave the remaining 3 cards, and then again I will have 4 positions what to choose from to reinsert this orange one. So for example, I can put it at the bottom, and then I can remove the green one. That's what would happen next. And here I've chosen to put it back also at the top. That's allowed. So between steps, you might not actually see any change, because if you take from the top and put back at the top. Okay, so this is a Markov chain. Okay, and the way to see that is, let me write xt for the order of the cards after t steps. And this is going to be a random variable, because at each point, there is 4 choices of where I can put back the card. Right, so yeah, so there's this that is displayed here. Each of these steps only happens with probability 1/4. Okay, and why this is a Markov chain is because it is memoryless, meaning that if I wanted the probability distribution after 3 steps, then all I need to know is what it looks like after 2 shuffles. Like the data from before is not useful, right? Because in order to do this 1 shuffle, all I need, I start from the state of the x2. Yeah. Okay, so the memorylessness property is what it means to be a Markov chain. So let's get some better notation for Markov chains. There is this curly x will stand for the state space. Okay, so that's all the possible xt's that you can have, basically. So in the example of the top to random shuffle of n cards, it would be all the possible ways of ordering these n cards. Right, that's just to write down all the possibilities. And then xt, each xt would be a random variable that gives you what the system is like at time t. Okay, and the memorylessness property means that you can describe the entire process by what's the probability of going from X to Y for all the X and Y inside the state space. And so assume as a very simple example, assume that you only have two states, like there's only two possible states that you can be in at any time. So then I can draw this matrix, and I just need to tell you what is the probability that I'm at X and I stay at X, right? What's the probability that I'm at X and I go to Y? Okay, the probability of going from Y to X and the probability of staying at Y. And then you can reconstruct the entire process from this information. So I just put all this information into a matrix, and my convention is that the starting state index the rows, and the ending state, the destinations, index the columns. Okay, let me show you like a bigger example. So this is for top to random shuffle of 3 cards. So how you read this matrix is that if you started as red, orange, green, okay, then what you would do is you would remove the red in the first step, and then you would put it, you can put it at the top, right? It is, once you remove the red, there are 2 cards left. So if you're counting gaps, there are 3 gaps between the 2 cards. And so each of the positions that you can reinsert will all happen with probability 1/3. So you can put the red back at the top, or you can put the red between the orange and the green, which would result in this one. Or you could put the red at the bottom of the pile, which would result in this one. So that's why in the matrix, there's a 1/3 entered in these 3 positions. And then where there's a blank, these are zeros. Okay, let's look at another line like this line, where if we start from orange, green, red. Okay, so the first move would remove the orange, and then maybe it puts the orange back at the top. So this is why there's a 1/3 in this one. So it's expressing this 1/3 chance of going from this one to this one, which is actually the same. Okay. Or you can put this orange one in the middle between the green and red, which would result in this one. So that's why there's a 1/3 here. Or you can put it at the bottom, so that would result in this one. That's why there's a 1/3 here. Okay, so notice that because I'm using 3 cards, the possible orders of these 3 cards, there's 6 different ones. And so that's why the matrix is in the rows and the columns of the matrix are indexed by the 6 possible orderings. Okay, so this describes the probability of going from one state to another state within 1 step. And you might be interested in what about transition probabilities across many steps, right? It turns out if you want to know, like after R moves, okay, so you take the top card, put it somewhere, repeat this R times, then what's the probability of going from X to Y? This is given by raising the matrix, raising this matrix of transition probabilities to the power R. Okay, so now you see if I want long-term behavior, that means I want R to be very large. This is related to high powers of the matrix. And that's why the eigenvalues and the eigenvectors become important, because they're related to high powers. Okay, how's it going so far? Does anyone want to ask anything yet? The people who are happy are the people who know about this. Okay, I'm gonna say like what you might want to learn. Okay. So what questions that people might ask about Markov chain? Yeah, if you anytime in this talk, if you think of something that you want to ask, just put it in the chat. Okay, if it's a bad point for an interruption, then I just answer you later. Okay. So what you might want to ask about this Markov chain first is what is its limiting distribution? Meaning, if you look at the probability of that at time t you are at state x. Okay, so the order of the charge is x. Okay, so this tends towards some sort of number. Okay, in fact, it does for random to top to random shuffling, because like you shuffle because you want to mix the cards, right? So you're hoping that after you do many steps, all orderings of the cards would be equally likely, right? So that means that for the case of card shuffling, this should be an x. Yeah, pi x is what I mean. Yeah, so there's a different number based on where you want to end up. Yeah, so the pi x is going to be like 1 over n factorial. So it says n factorial chance of ending up anywhere. Okay, don't worry too much about this part, because this part is about eigenvectors. So I'm not actually going to say a lot about this part. Okay. But I want to say, like, this equation is how we find what the limiting distribution is, and it's actually an eigenvector equation. So it's like one example of why eigenvectors are useful. Okay. And also, people also ask about the convergence rate, meaning what value of t do I need so that the distribution at time t is within epsilon of the limiting distribution. And this is answered by the eigenvalue of that is largest after 1. So 1 is always the largest eigenvalue of the transition matrix, of the matrix of probabilities. And the second largest eigenvalue is the one that gives you information about the convergence rate. Okay, so I want to look at this all algebraically, which is basically, I want to think of this matrix as the matrix for some linear transformation in some basis. Okay, so this matrix is okay. So it needs to be transposed, but that's just a technicality. What I mean is, I want to build a vector space. So first of all, like if this is to be a matrix of a linear transformation, then you know that what indexes the rows and the columns, this should be a basis of the vector space, right? So if this is to be the linear matrix for linear transformation, then its domain and codomain is going to be like formal linear combinations of these 6 things. Okay, I'll explain more in a minute. What I'm saying is, so you make a vector space V where the X is the set of states is a basis. Okay, and you code up this linear transformation such that this very important relationship is true. That the probability of going from X to Y is the coefficient of the destination in the linear transformation applied to the source. Okay, so if we started in the rainbow order, okay, and I did 1 step of top to random, then these are the 4 possibilities that can happen. And they all happen with probability 1/4. Okay, and so I define T of this deck to be the sum of the 4 possibilities with coefficients 1/4. Okay, so this doesn't really have any meaning as a sum. It's just I'm using a linear combination to record each deck ordering has a number attached to it. Okay, it's just allocation of numbers to decks. I just write them as coefficients. Okay. Okay, so bear in mind that this linear that if you think about the same linear transformation, but you use a different basis, it's going to give you like different probabilities, right? So I just said like, if you have, okay, maybe I should say that later. Okay, so as I said at the beginning, this perspective has been done before, and some successful examples are like random walks on groups. So how that, I'm mainly going to talk about Hopf algebras, so I'll just talk quickly about the group situation. I want to say it though, because it's things are like much simpler when it's with groups. So in the group situation, X is a group, okay, your set of states, your set like, the group situation actually applies to top to random shuffle. Because you can think of these deck orderings as the symmetric group, for example. So your set of possible Markov chain states is a group, which means when you want the vector space with it as a basis, that vector space is going to be the group algebra. Okay, and the linear transformation T that gets analyzed in this theory is that it's multiplication by some element of the group algebra, and then the algebraic facts that help with studying the chain, these comes from the representation theory of the group. Okay, and then this whole theory was then generalized to monoids. And what I want to point out here, even though this is quite different from the Hopf algebra setting, there is one thing that is similar. Okay, which is that V is not just a vector space. V is a vector space with some structure on it, and T uses that structure. That's the case where you can like get the most mileage out of this view, because this allows you to study lots of different linear transformations at the same time, not just your particular T on this particular V. Right? And I should mention that Jason Fulman also did studied some Markov chains using this perspective, and the algebraic object that he uses is called a dual graded graph, and again it's a vector space that has structure maps on it, and you can make the T linear transformation out of those structure maps. Okay, so how does the Hopf algebra story work? So, I should point out, so in these examples, right, I have a choice of V. V is a group or a monoid or a Hopf algebra, but I can choose different Hopf algebras, right? And if you use different Hopf algebras, the Markov chain is going to be on different objects. And if you also have a choice of T. So if you choose different T's, then it gives you, if you choose the same sort of object and so you choose the same structure for V, you can choose different T's, which will give you different Markov chains on the same type of object. Okay, so in this case, if you choose T to be multiplication by different elements, then you get different sort of card shuffles. Okay, so like card shuffling corresponds to this particular group of the symmetric group. And you can, so I'm going to study this using Hopf algebras. So the Hopf algebra that corresponds to this is Rie's shuffle Hopf algebra. So you are, so to do this, we are, I'm going to write S for this algebra, and the N is just indicating the degree, because this is a graded algebra. And N is just the number of cards as we saw before. So like this sort of thing would be in S3. And notice, different from the symmetric group case, I allow multiple cards of the same color here. Being a Hopf algebra, it means it has to have two operations. Okay, so the first is a coproduct operation, and this explains how to break an object of size I plus j into an object of size I and an object of size j. Okay, so these are linear maps. Okay, so I'm just going to describe how they work on the basis. how they what the images are on like actual decks. Okay, and I'm mainly interested in the case where the I is 1. So I'm going to divide the deck into a deck of size 1 and a larger deck. And this is just take off the first card and put it on in your left hand, and hold the other cards in your right hand. Right, and then the second operation on a Hopf algebra is product or multiplication. So this tells you how to combine a deck of size I with a deck of size j and output a deck of size I plus j. And again, I would only look at I equals 1 for the moment, which is, how do you put this deck of 1 card into this larger deck? And the answer is you can put it anywhere between the cards and you just add up all the possibilities. And this is why I need to allow decks to have multiple cards of the same color, because there's nothing stopping me from having a red card in both of these decks that are being multiplied. Okay, but that's just a technicality. So I'm sure everyone can see, if you think about it a little bit, I'm going to do an example. So if you don't see yet, you will in a minute. Okay, why? So it's why these operations are relevant is that the top to random shuffle is corresponding to the linear transformation that is coproduct, then product, then divide by the number of cards. So under the correspondence between the linear transformations and the Markov chains via the matrix, right? What corresponds to top to random shuffle is this linear transformation. Okay, so let's, as I promised, we would run through that. So, okay, I have to do coproduct first, which will remove the card. And then I do product, which is going to reinsert it in all the possible places. But the correspondence says that the output of this linear transformation should be the sum of all the possibilities with the probabilities as coefficients. So then that's why I have to divide by the number of cards to produce the 1/4 that are here. Oh yes, this. Okay, so the comment is that this should say n-1. That is correct. Yeah, thanks. I will fix it before I put the slides up. Okay. Okay. Quick digression so that I can show you a little bit of the eigenvector stuff. I said I wouldn't go too much into it, but I'll say a little bit, which is that so for this I need to rewrite the decks into numbers. So I just write 1 for red, 2 for orange, 3 for green, and 4 for blue, and I do the same for all of them. And okay, maybe they look more like symmetric group elements now. And this allows me to define a descent, which is a large number followed immediately by a smaller number. So I highlighted them here. It's like 2 before 1, and then 3 before 1, and then 4 before 1. Okay. And if you look at the subdominant eigenvector of this linear transformation, it tells you that after T top to random shuffles, the probability that the bottom 2 cards are a descent is this formula. So this is an example of what you can do using these eigenvectors. And this is a convergence rate result, right? That's what I said happens with the subdominant eigen data. Because this is going to converge towards 1/2, right? Because this fraction is less than 1. So when I raise this to the power t, this is going to go to 0. And so this is telling you like how quickly does this go towards the value of 1/2. So if it is not near 1/2 yet, then you know that you're not really randomized yet. So that's why it helps measure like how fast the randomization is happening. Okay, that's the end of the first part of setting up the connection. Remember that you are free to ask questions all the time in the chat. Okay, so I'm gonna call.
May I ask a question?
Yeah, ask.
So could I also look, for instance, more general multiplication? I could take out 2 cards or 3 cards at the same time and then put them back, or is it?
Yes.
It to be okay?
That is a great question. Okay, so 1n-1 is the easy one to analyze, the easy one to describe. So because it has a complete eigenanalysis. So it's true that I can do coproducts ij and multiplication ij for any I and j, and I can even take a linear combination of those things, and they will work with everything that I show here, apart from stuff like what's the subdominant eigenvector, because I don't know in that general case. Okay, but definitely I know the eigenvalues we know, and the projection stuff is all going to work, and of course the correspondence to a Markov chain always works, because I said you can do this with any linear transformation, that as long as pretty much the only condition you need is that it gives it expands positively in some bases. Okay, there's a question of, is it obvious there's only one subdominant eigenvector? In fact, there is not only one subdominant eigenvector. There are many. They give you different information, but this one is one that's sort of easy to write down. Sometimes they get a bit complicated. In this case, I know all of them, but this depends both on the algebra and on the function. Like if you give me a slightly messier algebra, I won't be able to write down any subdominant eigenvector. Or if you give me a different function. Is there a Hopf algebraic reason for the convergence towards 1/2? There isn't a Hopf well, the easiest reason is a probabilistic one, right? It's like you're converging to all orderings are equally likely. So if you look at the bottom 2, it's either in this order or it's either like large on small or small on large. So that's why it's 1/2. I don't know a Hopf algebra way of explaining this. But I also think that this may be obtainable. The eigenvectors and stuff might all be obtainable without using Hopf algebras. The top to random shuffle is very well studied using symmetric group or using other things. There are like tons and tons of things that which allows the study of this. Yeah, you definitely, it's definitely kind of overkill to do Hopf algebras here. But the nice thing is that when you do the same analysis with a different Hopf algebra, you see formulas that look very similar to this. So it's sort of giving you a uniform way of deriving formulas in all different things. Okay, so let me talk about the projections. So what's a projection of a Markov chain is? This is the question I want to answer. Okay, if X is a Markov chain on this state space curly X, then suppose there's a function on this space going to some other space. And I want to know, if I look at just the outputs under this function, do I see a Markov chain? Okay, as an example, suppose I'm colorblind, right? So the orange, the green, and the blue all look the same to me. So then I'm only marking where is the red card, right? So my function is look at the position of the red card, right? And I can ask if where is the red card at time t plus 1 depend only on where is the card at time t, right? That's the definition of what a Markov chain is, the memoryless property. Right, of course, the full order of the cards at time t plus 1 depends only on the order of the cards at time t, right? But that doesn't mean if I only look at where the red card is, that I can get this information only out of red card information. Maybe I need to know the full order of the deck at time t. Okay, so this is the question that is being asked. Is this chain, is this image chain a Markov chain? And if it is, this is called a projection of the original chain. So it turns out this is actually a projection. So if you think about it, if the red is on top, then I will remove it and then I will reinsert in all the possible positions with uniform probability, and this doesn't matter on what the colors of the other cards are, right? And if the red is not on top, then I take the top one, and then I can think about where that gets inserted and how this would affect the red card. But like where this top card gets inserted it doesn't depend on what colors the other cards are. So it never matters what color the other cards are. Okay, so there's like an elementary argument for why this does create a Markov chain. But I hope you are somewhat convinced that this is not always true. It depends on which function we're looking at. So this question has been around for a very long time because maybe this image chain is simpler in some ways. For example, the possibilities are much fewer, right? Now you're looking at only n possibilities instead of n factorial possibilities. So maybe it's easier to analyze. Maybe it has some nice properties, some additional theorems apply there, and this will help you deduce something about the original chain. So that's why people have been interested in this question. And there's actually a simple criteria to check when it's a Markov chain. So it's this Dinkin's criterion, and it says, look at the probability of going from x to y, and sum this over all y's that output the same value under your function. So this is basically trying to figure out the distribution of theta x at time t plus 1 as a function of x. But you don't want it to be a function of the source, right? You want it to be a function of theta of the source. So the criterion is that this should depend on theta x and not x. So this is like really just rewriting the definition. Okay, and what I mean by this is that if you have two different x's that output the same thing, then this sum should be the same. Okay, and this sum actually is the probability of moving from like the theta of the x to the theta of the y. So the lump, right? This projector chain is a Markov chain, so it's also described by a matrix of transition probabilities, which are these sums in the matrix. So this is an old question, and the question I want to ask is if x comes from a linear transformation in the way described before, what does Dinkin say about the linear transformation? What's how do I translate this condition into a condition on the linear transformation? Okay, and the idea is that you have a quotient vector space V bar, and let theta be the quotient map. Okay, you require two things. The first is that theta has to map the basis of V to the basis of V bar, right? Because otherwise, like you can't make the function on the Markov chain, right? So this is not thinking yet. This is just saying that the quotient map needs to be the linearization of a map on sets. Okay, and then the thinking translates to the second thing, which is that T has to commute with the projection map in some way, and in a way that actually produces a T bar on the V bar, and this T bar is going to correspond to the projected chain. And yes, I know it looks complicated, but I'm about to show you some examples where it's not so complicated. So remember, I like the cases where V is an algebraic structure, not just a vector space. Okay, and T is built out of those structure maps, in which case 2 is just true because theta has to respect the structure maps, and so everything just works. So what I mean is, if X is a group, okay, then X bar is a quotient group. Okay, and then if T is multiplication by something in the group algebra, then multiplication commutes with the quotienting of the group, like just it sort of, because everything is defined, because the T and the quotienting are both defined using the group data, like this has to be true. You know, and the first thing also has to be true because like the projection map is going to send the group to the quotient group, right? The elements to the elements clearly. So this, if you can extend this slightly from quotient groups to coset representatives, and then exercise 2.9, example 2.9 of my paper actually does out this example. So if you just trap the red card that this is a projection, is because you're taking coset representatives of S3 inside S4 is what's going on here. Yeah. So what does it look like for Hopf algebras? Okay, but I swear, like whatever your favorite type of algebraic structure is, just take the quotient of that algebraic structure, and as long as T is defined using that algebraic structure, these things are just going to work. Okay, so I like the case where V is a Hopf algebra and V bar is like a quotient Hopf algebra, and T is, well, is this thing that describes top to random, or as we just said, any linear combination of things that are built with the structure maps, right? As long as T is built using the structure operations on the Hopf algebra, this is going to work. And this is the same as T bar as the linear transformation you will define on V bar, because V bar is also a Hopf algebra, so these operations also exist there. Okay, and then because everything's defined in terms of Hopf algebra operations, the second thing is trivially true. And then you just have to check the first thing, which is that the basis you want, the basis of V that you want to define your Markov chain under the projection, it has to go to the basis of V bar that you want to define the Markov chain there. So this is satisfied for lots and lots and lots of quotients in the literature, actually, because usually your basis is some set of combinatorial objects, and so your theta map is like forget some part of the structure, and so it gives you another combinatorial object. So there are many examples that you can apply this to, which unfortunately I can't show you because the many examples of quotients that exist already, that for which this whole thing works, those Hopf algebras and the related Markov chains take like a long time to describe. So that will be in like the advanced part. And maybe I'll just show this. I'll just show this example. So
Amy,
this is
Amy, sorry,
yeah?
There is a question in the chat.
Yeah, so the answer is I don't know. So that's why I decided not to say anything yet. I mean, we can explore about that. Yeah. So here I recover a result of Athanasiadis and Diaconis that if you look at the descent positions on the top to random shuffling, it gives a projection. And the so this involves building. So why I said this is not really an example of what I was trying to say, that you just take like any example that exists in algebra and it would just work, is that I actually had to build this map, and this is a very non-standard quotient map built explicitly to prove this theorem. So the S is the shuffle algebra representing the top to random shuffling, and you map it to quasi-symmetric functions, which mapping to the fundamental basis corresponding to the descent set, and that's going to give you, if you use this or any variation of this on quasi-symmetric functions with fundamental basis, then you will get the Markov chain that is being projected onto. And this is where the basis condition comes in, because quasi-symmetric functions have lots of different bases, but you have to use the fundamental one because that's the one that's the image of this. So so I think the more interesting theorem is the case of subspaces and subalgebras, because they also induce projections, but it's much more complicated. And again, there is some theorem like the Dinkin thing, which applies to all Markov chains, that I then translate into the language of linear algebra. But in that case, the analog of the Dinkin thing is not even well known. So that's an even more obscure thing, that you can do something similar with subspaces and subalgebras. And again, there's a condition on the basis and a condition about the commuting. I want to say a little more. I hope it's okay to go a little bit over 50 minutes, because I was taking questions in the middle.
Sure.
Okay, we'll go a little bit more. I want to go into the advanced thing, because there's something that I think that I'm surprised no one has said yet. But okay, so I want to do one more example, which is on partition shapes. Okay, so something like this. So in terms of Hopf algebras, is the algebra symmetric functions, and I'm using the Schur basis. Okay, so I'm looking at left justified diagrams, and each row has to be the same length or shorter than the row above. Okay, so I'm going to use the same sort of coproduct product maps as before. And coproduct is remove a box, and any boxes that leaves you with a valid diagram is okay. So here there are the three possibilities. Okay, and the product is to add a box, and again, as long as after the addition you have a valid diagram, then it's okay. So maybe I show you. Maybe I show you on this one. Like here, I can add here, or here, or here, or here. Okay, those are the only 4 possible places where you can add a box and still be left with a left justified diagram that has non-increasing rows. Okay, so I want to look at what the Markov chain on this is going to do. Let's do smaller example. Okay, that one's huge. So I'm going to compute coproduct, then product, then divide by n, which here is the number of boxes. Okay, so if I do coproduct, so there's only one removable box here that leaves me with a valid diagram. So it gives me this, and then I have to add this box back to back to the rectangle shape. And there are 2 ways to do so. I can add it at the end, or I can add it below like this. Both of these are legal. and then I divide by number of boxes. So this is telling me that if I start from the 3x1 rectangle, then the probability of staying there is 1/3, and the probability of moving to this one is 1/3. And this is problematic because they don't add up to 1. But that can be fixed by multiplying by this number. Okay. So there's some function eta, which is the number of ways to split your basis element into singletons by repeatedly applying the coproduct thing. And you need to multiply by the by eta on evaluated at the destination and divide by eta evaluated at the source. And okay, for reasons of time, I cannot go into this too deeply of how to calculate this. It really is not easy, but it's going to take me like 10 minutes. I mean, it is not hard, but it just takes like 10 minutes to explain. Okay, but what it does is it gives you an extra 2 here because the eta of this shape turns out to be 2. And so this gives you a probability of 2/3, and so you're fine. And why this is the right thing to do, and this is how you do it in general if you're not on a Hopf algebra, okay? And why this is the right thing to do is because it keeps the transition matrix being the matrix of a linear transformation, of the same linear transformation, but in a different, in a scaled basis. So it does not break that connection between the linear transformation and the Markov chain. And so the eigenanalysis and the projection theorems and all those things still work.
So can I ask a question?
Yeah.
So at the level of the chain, does this have an interpretation as some sort of conditioning? So this kind of factors eta of y divided by eta of x you would see when you're defining some sort of a conditioned Markov chain on to some event.
In some sense, this exists to make sure that the chain gets defined.
Mm-hmm. Yeah. Okay.
I mean, you can interpret this in the chain because if you want, if you want to explain it in terms of the chain, you can say that you remove a box, and the probability that you choose a particular box is related to these etas. And then you add a box, and which box you choose is again related to the etas. So if you want to understand, so that's how I would explain what the chain is.
Mm-hmm.
So all of this is, yeah, if you have questions, you should tell me, because like the paper is very long, and I can point you to like where the positions of all the particular things are.
Okay, so maybe we can discuss it later. So I'll let you finish your talking then.
Yeah, it's true that I wish I could give like a longer exposition of how this part works. There's people asking about advanced things. There's like one more page of advanced things, but that's very fast. But this, if you want to see in detail how this works, I don't know. I mean, I'm happy to show you, because this is probably sort of necessary if you want to run your own Markov chain.
Yeah, I mean, if you can.
I don't.
Then,
I know that some people have to. Maybe I'll say like a 20-second thing, and then people who want to know more can chase me down like whenever. Which is, in the general case, you need to look at the dual map to your original linear transformation. Okay, and you take an eigenvector of it of maximal eigenvalue, which must be 1. if your maximal eigenvalue is not 1, divide by something so that it is 1. Okay, and it's a dual basis element, so it's going to be like it's going to be a function, and that's the function that you use to do this.
Okay. Okay.
Yeah. So I should stop. Yeah.
Yeah. Thank you.
You're taking a, okay.
Yes.
Applause break. Okay.
So thank you for your talk, Amy. And are there any more questions from the audience?
Yeah, so maybe I can ask my automaton question again, because I also now looked at your paper in parallel. So you have this lumping operations, and it sounds really like what? Yeah, so you have a subsystem somehow, right? You have a Markov.
The lumping is the same as the projection thing.
It's the same, yeah.
Yes.
Yeah, so this feels like, but maybe I'm wrong. So it's
just another like word. Like probabilists say lumping a lot, because it's like they think about it as identifying the bunch of states together of the pre-image.
Yeah.
So they call this a lumping. Yeah.
Okay, so this is very close to automaton theory then. And then is the other way, did you investigate the other way around also? Like, for example, you can lump, for example, let's say you have a complicated thing and you lump it in 2 ways. Then sometimes it's possible to go back from the 2 lumped systems. Does that make sense? So if you have 2 coarse grainings, together they give you the whole system.
I don't know. I would believe there are many different lumpings that you can do of a Markov chain. And if you just see 2 different ones, can you reconstruct the original? I'm not sure.
Or maybe a follow-up question. After you've done the lumping, so what can you then do with it? Why do you do this lumping? Yeah.
I don't have any simple examples. I have an example that takes 5 minutes to explain, which I think I should not do right here. Usually it's because the lumped, so it's usually, I think it's because the lumped chain has some extra properties that the original chain doesn't. And you can, so maybe it's a bit easier to investigate things like the convergence rate on the lumped chain. And then if the lumped chain converges slowly, then the original chain also converges slowly, right? If the lumped chain converges quickly, then you can't really say what happens on the original chain, but it gives you some information like that. And oh, the eigenvectors lift. So if you have an eigenvector, so I said that this is a subdominant eigenvector of this map on the shuffle algebra, but it's actually computed just in terms of the sets, right? So in fact, one way you could obtain this eigenvector is by looking at the chain that's lumped to the sense, and then you just pull back.
I see. Okay, that's a good motivation. Yeah, thank you. Yeah.
Yeah, and then there is like the complicated thing.
Okay. More questions? There's another question.
Oh, are the eigenvectors of top to random known? What does in general mean? You mean for different Hopf algebras, or?
Well, I mean, for this one, you seem to have like this eigenvector to have a subdominant eigenvector. Yes. Do you have all the eigenvectors?
Full eigenbasis. I have full eigenbasis. So you can do, so this operator, why I like to look at this one as opposed to linear combinations of the other types is because for this one, if the Hopf algebra is commutative, or co-commutative, so you have to do this one, the eigenvectors have to be on the dual, right, to do this, because it's a right eigenvector, okay? So the dual of this is commutative and the dual is co-commutative, right? And if you're on a co-commutative and this is your operator, then there is a basis of eigenvectors that you can just write down. Yeah. Or you can, okay, so for shuffle algebra, you can't, but in lots of cases, you can do this thing using dual graded graphs instead. And then there is another formula that will give you like an eigenbasis.
Okay, I see Kurush has a question.
Could you, so where exactly is the shuffle structure entering? So the shuffle product. The moment
the shuffle structure is in if you want to multiply like larger decks, then what happens is like you have to, so if you have to keep this deck and this deck in the same order, so it looks like you're doing this, and so that's where the shuffling happens.
And so where I come from, usually we think in terms of shuffle, and the next thing that's related to it is the quasi-shuffle, when you start to stick or glue cards together, when you have an extra structure on the
yes. So
yes.
Yeah,
sorry.
so Percy Diaconis, who was my advisor, said recommended the same thing, right? So what happens if some of these things are stuck together? So first of all, that's not graded, but that's okay, because you can just change you can just change the V to be like filtered or something. But then actually there's a trouble, which actually that's a great question for me to point this out, which is that sometimes the ethers will turn out to be 0. Now you're screwed, because now you can't rescale, right? So when I said you can, so I was kind of surprised when I said you can do this with any linear operator, and no one asked about like the coefficients being not summing up to 1. But the fact is, then I was like, oh, you can always rescue this, but you can't if sometimes this turns out to be 0. Then you just can't rescue it. So that's what happens.
Okay.
If you use a quasi shuffle.
Thank you.
Okay, any more questions?
I have a question.
Yeah.
A quick question.
Yeah, Nick.
Hi. It's about the operator T, instead of taking coproduct and then product, you take any n power of the convolution of the identity. Means
yes,
the product.
You can do that.
Yeah, how do you look at that in general, and also what happened for the antipode? I mean, looking at the antipode as the case -1 of so the antipode is the inverse of the.
Is the antipode positive? You need positivity. I can't fix that. I can fix the not adding up to 1, but I can't fix the positivity. I'm not. So the antipode might do a different thing. But okay, so I said any linear combination. I said I can do any linear combination of these maps. And if you're saying, you can split into more than 2, if that's what you are asking. So if you wanted to do like convolution of the identity, that would be splitting to like many pieces and then putting them back together. So this is not restricted to 2 pieces only. There's no difficulty to generalize. And what can the antipode do? So the antipode for shuffle algebra is reverse, right? Is that correct? Okay. So reverse is, okay, think of reverse as an involution. You can do this, so you can split. Okay, so and then you can flip, and then you can put it back together. Okay, so not in these 2 papers, but in an upcoming thing, you can I have eigenvalues of all of those things. But any sort of like any involution that interacts correctly with the algebra will do, with the product and coproduct. It doesn't require to be antipode, but I guess that is where the inspiration came from. I don't know what else is good to do with the antipode.
Okay, I see that Hans has a question as well.
Yeah, I wondered, can you say anything about entropy of shuffling processes by this kind of approach?
Entropy?
Yeah, I mean, the way that disorder is how disorder is growing when you are shuffling things and so on.
The number of descents increases. That I know. Does that sort of make sense?
Yeah, it might be a stupid question, but I recall there was quite a lot of discussion about this kind of shuffling processes where essentially the deck was ordered or until a certain point where it became very unordered, approximately if you do like log n shuffles. At that point, you had a kind of a cutoff where the entropy was growing extremely fast. So I don't know if this kind of analysis can also give more light on this kind of entropy growth things in shuffling processes.
I think you know more than me.
No, I don't know. That's okay.
The algebraic method is, I have to say, it's not. I think it's not very strong. I think like for things like obtaining like convergence and stuff like that, I think like some probabilist, like definitely for like cases of shuffling, probabilistic techniques are going to like completely ace any algebra, like any algebra thing done this way. Because the algebra is very rigid, right? So you can't really make a lot of approximations and that sort of thing, which people do. Like the only way I can say is if you look at the number of descents, the number of descents increases as you do more shuffles. So one way of seeing why like this is not, why this takes a very long time to mix, is that like you gain descents slowly. It's something like that I've heard.
Okay, thank you.
Yeah, Kurush has another question.
I vaguely remember in an old work by Patras from '93, he looks at this combination of co-products and then shuffle products, and he gets this 1/2, 1/2 to the weight of the word. Is there a connection?
1/2 to the. Okay, so I use some things about Patras, yes, because Patras basically looked at these things, right?
Yes, yes.
And he explains like how these things compose and all that. Yeah. So that definitely gets used a lot in doing this. But I'm not sure. What do you mean by this 1/2 to the weight thing?
We used something of a similar result of when you combine the deconcatenation and shuffle product, and then usually you get 1/2 to the weight of the word or the depth of the word times the word. Such a result if you apply this to a word. It's something what I vaguely remember, that there's a factor 1/2 coming in naturally in this operation. But I may confuse myself.
I don't know this part.
Okay. We used this in another work, and it was quite helpful there somehow. That's what I remember. But we can discuss this.
Yeah. Do you have a reference for this thing? I would be very interested in how it works.
Paper.
So you're saying in Patras's paper?
Yes, I can put it.
Yeah, I am.
It's in this paper.
Thanks. Yeah, because I don't have my papers here. Yes. This I remember reading this. This one, like around where?
Now you put me on the grill here. Okay, maybe.
We can talk about this thoroughly later.
Yes, I think it's
1.5.
yes.
Yeah, this paper is really interesting because then it does like Adams operations and which is what Yannick was talking about, which is like splitting into more than n parts and like splitting into more than 2 parts, and then that's all. That's sort of where it started. If you read my like old stuff.
Sorry, what are you looking for?
There's some like 1/2. Okay. I'm
1/2 of what?
I'm just okay now. We use this result in another paper where we just really look at this operation deconcatenation followed by shuffle, and then we essentially use that this is essentially 2 times the weight of the word times the word then itself. But now it's something that just come to my mind. It's a while ago, so I would have to rethink it a little bit. But
what's the weight of your word?
The length, the number of letters.
Oh. Wait, but isn't the number of letters constant when you do co-product and product?
Yes.
Okay. Are you saying that is this something to do with the fact that 2 to the n terms appear if you do like all deconcatenations and then all shuffle?
Yeah, it's a full deconcatenation and the full shuffle product.
Yeah,
yes.
and then okay,
yes.
So you're basically saying you want to do this. Right, you want to do co-product then product.
Yes.
Then you have to divide by 1/2 to the n. Yes.
Yes.
Right, because I said you have to scale out so that the maximal eigenvalue is 1. So the correct thing to scale out by is 2 to the n.
Yes. Yes. Yes.
Okay. Yeah.
Okay. So if there are no more questions, I suggest we thank Amy again. So maybe we could just commit
Thank you guys
clap.
for coming. Thanks, especially to people with cameras on, because that always helps me a lot. And thanks you for all the questions.
Yeah.